Morning, guys. If you haven't done so already, if you wouldn't mind letting me know in the chat that you're here. I'll quickly take attendance and let's talk about what we're up to today. I believe we've only got 2 days left, including today. I mean, of actual class anyway, like lessons. Okay. So, as I mentioned, we've got 2 days left. Today, tomorrow, where we're going to finish off our evolution unit. Just as normal, tomorrow is the last day of the unit, which means that you hand in your vocab list when you're done the day. And there is a quiz. Just like the previous quiz, a little bit shorter than the previous quizzes. The unit was a little bit shorter. But there's also a quiz. It's open book. It's exactly the same as the previous quizzes. And then we're done. So if you decided that you did want to do the project, that is available to you. There is a little bit of time tomorrow to work on it if people are interested, although some people need to use that time to catch up on other things. But it's due, I believe, tomorrow at midnight is how I have it set up, which makes sense. Let me just double check that. So I couldn't delay it because I got to get them marked right away this weekend. So and then I got to start following up with some students that are still missing assignments. So that's the hardest part at the end of this course, I think. So where is it here? Yeah. Did I have the date correct? Yeah, Friday at midnight. So that's for the presentation. If you could do the quiz same day, that would be awesome. Realistically, if you're finishing the quiz by Saturday, that's not a big deal. I won't be like compiling those marks until the weekend. So if you need an extra day to do the evolution quiz, that's not a big deal. But hopefully you'll be done your vocabulary list. You should be, again, completing it as you go. So on the last day, it should be like, well, I'm done now, so here it is. So I have most people's plants vocabulary list. I'm still missing 6, which is not great. So if that's you, you need to hand that in immediately, okay, right away. I'm trying to get those back to people, and like at this point, like we're well past when you should have handed that in. So plants vocab list has got to come in today. Your importance of plants presentation, I'm still missing 11. If you got to finish that, guys. So if you're having technical problems, you're having problems finding sources of information or whatever, like let me know. But you got to get that stuff in. I got to get them marked like ASAP. So please get those in if you haven't done that already. And there are only a few people that haven't written the plants unit quiz, but if that's you, you have to get that done now. So don't put it off past today. Make sure that you get the plants quiz done. You shouldn't have to still work on plant stuff after today, because we're going to start tying up the evolution unit tomorrow. The evolution unit's over tomorrow. Tomorrow's the last day of class. So just don't put yourself in a bad position here at the end of the semester. I know the deadlines have been tough for the entire quad, but you kind of got to pull your pants up here, guys. We're really coming to the end, and I need all of these assessments at the end in order to get you a credit. I've already like minimized the number of assessments in the course as much as I possibly can. Basically the minimum set that I could have and still attempt to assess you on all of the like key learning objectives from the course. So if I start taking those out, I simply don't know whether you got parts of the course or not, and I have to be able to like back that up with evidence when I assign a credit. So basically you're tying my hands, so don't do that, please. If you're really in trouble, you've got something going on at home, or you're getting in trouble with regards to like timelines here at the end of the year, please email me. Okay, let's discuss what an extended timeline should look like. I'm not mad. Like it's not personal. I need to get this stuff from you in order to get you a credit, and I really don't want to have a conversation with people next Tuesday saying, oh, you owe me these 2 things. And I know that this happened last quad too. People are going to say, well, I just need 1 more day to finish this. It's like, my report cards are due, guys. I don't have 1 more day to give you. Like this is over now. So it's not that I don't feel bad. I feel very bad. I do not want people to miss out on getting this credit, especially if you put in a ton of work, and everybody's done that so far. So just if you're in that position now, like you got to start getting stuff in like immediately. So I'm not trying to give anybody like a particularly hard time, but I am starting to get concerned with a few students. I know some people have owe me several things, but we've had a conversation about timelines. And if that's you, then you can just take a breath. That's cool. We talked about this already, and that's fine. But some people are sort of just in the ether, and I'm not able to get into communication with them, which is a little bit concerning. You got to get that stuff in. I got to see it. So anyway, I'll stop talking about this, but really, guys, like today and tomorrow, those are the last days of class. Monday and Tuesday are support days. So I will be working with students that do owe assignments at that point. We have to communicate with each other directly. Some people have been avoiding talking to me, and I understand that it's stressful. Hopefully not too stressful. I mean, I'm not upset. I just really want you to get the credit. So anyway, like I said, if you're in that position, we'll talk. But Monday and Tuesday are support days. There will be a survey available to you. I'll post it over the weekend. It'll be on the front page. There'll be a new tab on the content. You guys can't see this, but it is called Summative Days, and it'll have a link for a Google Meet in there. A Google Meet that I just leave open for those entire summative days. It also has the link on it for the survey. So that'll be popping up like pretty soon. And I just got to set the Google Meet up. But you guys can drop in during that time anytime if you need to complete stuff, if you still have questions. And I'm happy to answer your questions. It's not like I'm not going anywhere, but I will be assessing people's final projects that they're handing in, the Evolution project and stuff that comes in late. Hopefully there's not too much stuff coming in late at the last second, and I'll be writing your report cards. So and setting up for the next quad. I gotta get my classes ready for the next one. So anyway, let's get on to today's stuff. Just a heads up, and please communicate with me if you're falling behind, guys. We have to talk. Let me throw this up on the screen. Working. No, not gonna work. There we go. All right, right on. Okay, so today, in block 1, we're going to be talking about patterns of evolution. So by that, I mean when things do evolve, there are some general patterns that can be seen in populations as a result of the selective pressures that we talked about the other day. So like these things lead one into the other. So the other day, we talked about different types of selective pressures. We talked about sexual selection, and then disruptive, stabilizing, and directional selection. And when those types of selective forces are acting on a population, it leads to certain patterns that are observable in the environment. Okay, so and those are listed right here: adaptive radiation, divergent evolution, convergent evolution, and coevolution. Okay, so those things are known as patterns in evolution. So just to give a quick example of what I mean here, divergent evolution is when one species diverges in terms of their physiology, because there are two. This happens due to disruptive selection, and so we kind of already addressed this in a way. When there is a selective force pushing in both directions on a population, where both extremes are favored. For example, let's say that it's useful to have a long beak because you can drink some certain nectar. And it's also really useful to have a very short beak because it's easier for eating these like tiny nuts that are found in your environment. But medium beak is terrible. So then oftentimes in the population you start seeing that's disruptive selection. So it's when selection is pushing you in two directions. And then that can lead to divergent evolution, where you see this one species is diverging into two. Okay, adaptive radiation is usually when a species moves into a new area, and there are a whole bunch of different evolutionary outcomes that would be useful in that new area. So for example, maybe it's useful to have a long beak. Maybe it's useful to have a short beak. Maybe it's useful to have a beak with a hook on it. Maybe it's useful to have a beak with the nose holes in a different place for breathing in the water. Maybe, like a whole bunch of different niches are acceptable. And in that case, and there's a little picture of it right here on the front here, you would get a divergence, in this case, there's a whole bunch of different diverging. This is called an adaptive radiation, into a whole bunch of different subspecies, which eventually could become their own species. So one type of bird could become 10 different types of birds because there are all these different niches that could potentially be formed in a new environment. Okay, and the example, they talk about Darwin's example when he observed birds on the Galapagos Islands and stuff like that. Okay, so those things are called patterns in evolution. They are what we see on a macro level in terms of how species change over time. Okay, so there's some, you need to know what those different terms mean: adaptive radiation, divergent, convergent, and coevolution. And you should be able to provide an example for each of those. It's kind of what we're looking for here. Okay, so there's a video that you watch. This is a pretty good video that talks about those different patterns that exist. Okay, you're going to read 8.3 in your text. You might want to consider making a study note from chapter 8.3. I don't specifically ask for it here, but again, it's great practice to do that. But you only need to read the section on adaptive radiation on page 341 and 342. Okay, all the rest of the stuff in that chapter in 8.3 is already covered in the previous video. They don't do a real good job of covering adaptive radiation in the video, so and which is why I have you read that part of the textbook. If you want to read the whole chapter, that's fine. But it's most of it, almost everything that they say, is covered in the video too. So it depends on what medium is more useful for you. If you prefer to read it again, or the video is better for you, then consider watching the video. Consider reading as well. Okay. Yeah, well, I mentioned that right there. Yeah, feel free to read the entire chapter if you're interested. Add any new terms to your evolution vocabulary list. So you got a new vocabulary list for this unit. And then there's some questions from the text, 345, number 1 to 4. They're specifically addressing these patterns in evolution, asking you, oh, what pattern of evolution is this? And which, what would be an example of this, or whatever. Okay, so it's all referring to that, those patterns in evolution. And then there's a little exit quiz at the end, again, just testing your knowledge on, do you understand which pattern of evolution is which? Okay, that's the first half. The second half is the part, I always struggle to find a good method for discussing this particular topic. I had a note that I did, but then I was just doodling around on the internet, just looking at videos and stuff, as one does, on YouTube and things. And I found a bunch of really, really good videos on human evolution. They're much more interesting than my note, and they cover all of the same information, plus a bunch of extra stuff that I probably wouldn't have covered. And then I looked back at the chapter in the text, and yeah, it's pretty good. These videos actually cover quite a bit. So really, what these videos are doing are summarizing chapter 8.7 in your text. So if you're like, blech, I just want to read the textbook, that's fine. You could read chapter 8.7. There's extra information in the videos. I highly recommend them. They're very interesting, especially if you're interested in how we got here, humans. I mean, for the most part, like, that's the reason that people get into the study of evolution in general, is because they're interested in our human history. And then they kind of expand upon it and say, well, what about ants or whatever? but in general, I feel like as a species, we're pretty self-centered. We tend to focus on our own history, and that's fine. I don't think there's anything wrong with focusing on human evolution. So anyway, it's a series of videos. There are 5, and as you're going through these videos, I have created a guiding question sheet. So the idea of this thing is this helps direct what I want you to know from each of these videos, okay? Because I mean, obviously, like any YouTube video, it's not like they're not like, here are the 5 things you need to know. They go all over the place. So I first of all, I give a list at the beginning, okay? these things are the things in general that you should be getting out of the video. These are, by the way, also the main highlights from the chapter in the textbook. Okay, so what I have here is, why is there no first human? Okay, so there's no such thing as, people always ask about this, like where was like the first guy? Where was the first girl? Where's she located? Like what year was that? That's not really how evolution works, because it's slow incremental change over time, right? I mean, we had ancestors and they had ancestors and they had ancestors, and they're changing over time. So there's no like line. There's no like, okay, here's the line, and then this was the first person after that, okay? And the first video goes into a really good detail, sort of explaining this and giving lots of examples about why you don't have like a first of a species. Like, that doesn't really exist. So anyway, a little bit, you should be able to discuss that. You should understand that concept, because that's the first part. Neanderthals, really interesting. Our closest relatives, well, we're our closest relatives, they're extinct now. What happened to them? Where do they go? What are some of the technologies or technological innovations that caused a rapid change in human evolution? So some of our cultural inventions as a species actually changed the course of our evolution. And what were those things, and how did they change human evolution? Okay, so that's in one of the videos. What's the relationship between modern humans and the other primates? Okay, so now I'm talking about the other still existing primates, monkeys, bonobos, gorillas, etc. So there's a video where they specifically discuss how we're connected to the other primates. We are primates as well. So how are we connected to the other primates? And the very last video has a really interesting topic where it's talking about the idea of collective learning. I put a link in there. It's linked to an article on collective learning if you're not sure what that means. They discuss it in the video too, so you don't have to look it up. But and how did that collective learning, which is unique to humans, how did it impact our development as a species? Okay, so those are some general things. Now, this particular day has a little bit of a crossover between, well, I guess history. I guess technically this is our history, but it also has a sort of a connection to anthropology and like the study of cultures and stuff like that. So this is not strictly like a by the numbers biology lesson. There's kind of a mix of stuff here, which is fine. I mean, biology overlaps with a whole bunch of different disciplines, but anyway, if you're as you're going through, before you watch each video, I have some questions here that you should consider while watching each video. Okay, I mentioned the ones at the top here. Like these are the learning goals. This is what you should be able to do at the end. But as you're going through, read the little blurb on the video and look at the question, then watch the video, then come back to your question sheet here. You should make a copy of this and answer the question. Okay, so why is there no first human? You answer that. All right. For the second part, you read the little blurb. Why are we the only humans left? Oops. No, that's not it. What is this here? Oh, sorry. Yeah, that's actually for video number 3. There's a few questions. Video 2, I mentioned here that this video is kind of just for fun. It's just an animation, so it just goes through an animation of different iterations of animals, and then it talks about different iterations of humans specifically based on the fossil record. So I don't actually have any questions for them, but it is cool. And then anyway, number 3, here are the questions. Okay, so you just go through and answer the questions as you go. Make sure that you, or at least I would highly recommend that you read the questions first. So read them before you watch the video, just so you know what you're looking for. It helps kind of direct your attention while you're watching. Okay, so you go through, you watch the videos, you answer the questions, and again, it covers the content in chapter 8.7 really well, and you don't have to read chapter 8.7. So and honestly, it covers it quite a bit better because it gives great diagrams and animations to like show how a lot of these like processes work. What did our ancestors look like? What's our connections with other primates, etc. Like it does a good job of animating those things. I'm a visual learner, and so for me, like, this is a lot better than reading the textbook. But like I said, if you want to augment it by reading the text, absolutely read chapter 8.7 as well. But you don't have to read chapter 8.7 if you don't want to. All the information's in here. And then when you're done, there's a little exit quiz. Again, just testing your knowledge on those little points they're mentioned at the beginning of the document. Okay, So that's it today. We're going to talk about patterns of evolution and human evolution. I will be here if you need anything. We're going to come back for attendance at 11:05 and do some meditation together. If you are, once you're done, if you are working on the evolution presentation, that's cool. Please do not work on the evolution presentation if you owe me anything else. Like I said, I'm still missing like 11 of the plants presentation, 6 of the plants vocabulary list. Like if that's you, please don't do the final assignment, guys. I need to get that stuff from you immediately. So once you're done today's content, you should be working on that right away and getting it into me. Okay, I got to start following up with some of you guys because I'm really worried here. There is a pretty hard cap at the end of this course, and a number of you are going to start running into that cap in very, very little time. So anyway, okay, let me know if you need anything, guys, and good luck. All right, guys, if you haven't already done so, if you wouldn't mind, please letting me know in the chat that you're here for the second half. Take attendance quick. Okay, I mentioned in the just in the chat, I forgot to mention this at the beginning of the day. If anyone has any questions from the content from the second half of yesterday, or first half of yesterday is fine too, or you have any questions from this morning's content from Block A, so that would be from page 345, number 1 to 4. You can let me know. I'm happy to review any of the questions from the homework. While I'm waiting for people to type in there, one other quick thing to mention. I got some emails about the change of the end date for the course. So you may have noticed that in Brightspace where it says course end date, it has been changed to the 10th of February, I believe. So just to be clear, that didn't actually change anything. Nothing has changed. I requested that they change that number in there. I don't have access to that directly, but I emailed the people at Brightspace and asked them to extend it. It's just so you are able to access mark postings and like final marks and whatever else from Brightspace after the original end date. So the original end date was the 2nd, I believe, of January, which is technically the last day of class. However, some people, especially people handing in late assignments, won't actually know their mark on that day because I haven't been able to compile it probably until the Wednesday when I've got to put your report cards in. So I ended up having an inability to give feedback to people that handed stuff in late at the end, which is a bit of a problem. So All that does is just allows you to access the course online after the actual last day of class, which is next Tuesday. So don't take that date to mean anything at all. That's all that means. It's not like the class is longer or there's more to do, or that's it. So nobody with questions from the homework? Page 345, 1 to 4. If you have questions from the second half, that's the human evolution component. Question 2, sure. We can definitely look at those at the beginning of tomorrow. Let's look at question 2. Okay, so what they're talking about here is this is another island scenario, Hawaiian island scenario, and they're talking about how a single plant. Let's see if I can throw this up here. They're talking about how a single plant can have a whole bunch of different offshoots on a particular island. They're called silver swords, and they are a number of different sort of subspecies. I guess they're new species because they can't interbreed any longer, and so there's a whole bunch that are descended from a single common ancestor found in an island environment. So island environments are ideal for this because you've got your island. This is obviously an exaggeration, but you got your island out there in the middle of the Pacific or whatever. Or this is Hawaiian island. So, and a new species of plant arrives somehow to the island. So, I mean, obviously we probably don't know the exact mechanism here, but maybe it hitched a ride on a log that was floating in the water, or a bird ate a seed on another island and then migrated to this island and then pooped out that seed. But somehow, a new plant was transported to this island. Okay, so we've got this like grassy plant that was transported, and because the island has never seen a plant like this before, there's lots of different potential niches that it could move into on this island. So, for example, and again, I don't know anything about silver swords specifically, but this is like a really general example of how this could work. So, for example, let's say that there are areas in the island that are really rocky. Okay, so you got a rocky area over here, and then you've got a muddy area. Some seeds are digested, Tamer. I can't remember how deeply we got into this in the plants unit, but flowering plants produce pretty hardy seeds. So, unless you are breaking open the seed as part of the digestive part, like breaking open the outer shell of the seed, often they are not destroyed by digestive systems in animals, or not all of them are destroyed. So some of them make it through because they're protected by a fibrous coat on the outside. So if you watch the documentary in the plants unit, they mentioned, I can't remember the example they used. It's where they shot like the seeds out of a musket, or out of like a shotgun or something. Like some of them have a very hardy coating on the outside that protects them from being digested, and that's actually part of the strategy that the plant uses to distribute its seeds. So when animals eat the fruit, often the seeds just go along for the ride, so they don't get digested, but the animal's not intentionally eating the seeds. The seeds are just sort of like part of the fruit, and then the seeds end up getting distributed for free, basically, by whatever is eating the fruit. So the fruit is actually a distribution mechanism for seeds for the plant. Like, that's why it's evolutionarily an advantage for the plant, because the more tasty the fruit is, the more its seeds get widely distributed, and so therefore there'll be more of that in the subsequent population, et cetera, et cetera. So there's a selective pressure towards having better fruit or more appetizing fruit, because that's a better seed distribution mechanism for the plant. So typically they're not digested. If the animal breaks apart the seed coat and eats the interior part of the seed, then obviously that part gets digested. But a lot of flowering plants have indigestible sort of a husk around the outside. If you think of like a sunflower seed, if you eat sunflower seeds and you don't bust them out of the husk, that they go right through your digestive system. So you can probably plant the seeds afterwards. And actually there's a number of plants that actually need to pass through a digestive system before they will germinate. And that is also an advantage to the plant, because the seeds that it drops right at its base, it doesn't really want those seeds to germinate, because those are the ones that are going to compete with it. It's going to have essentially its children overshadowing it and preventing it from surviving and reproducing. So it really wants the seeds to go through a digestive system first before the seeds become viable. And there are actually many plant species that require that. Anyway, sorry, we're getting a little bit off track here, but hopefully that answered your question. Let me see if I can try and answer your question, Evan, here. How one-sided can an evolutionary pressure be? This is hard to, I can't put a number on it, but when directional evolution is happening, let's say that there's a change in the environment and a strong selective pressure is placed in one direction, it's usually not directional forever. Okay, so like I'm going to use a classic example of a directional mechanism, and I've already used the neck example for dogs, but let's talk about it in giraffes. Okay, so giraffes have a really long neck, and part of the reason, oh boy, I haven't learned my lesson, and I'm still drawing. I'm still drawing things, even though I really shouldn't draw animals. Oh, that's not as bad. I've done a worse. I've done a worse picture than that. Okay, here's a giraffe, and if you think, like, one of the main selective pressures for giraffes is that they're being selected. Their neck selective pressure is saying, well, acacia trees. And this is an example actually of coevolution, because acacia trees have actually evolved to grow taller to avoid the giraffes. And so actually in some ways, Evan, the arms race, the competition in evolution between two species when they're co-evolving, sometimes that pressure never subsides. So I'm going to actually give another example afterwards here that of where there is constant selective pressure, directional pressure of a trait. Okay, but in most cases what happens is the animal, let's say we've got an acacia tree here, and this giraffe is eating branches off of the acacia tree. So in this case, there's a selective pressure for the necks of the giraffe to get higher and higher and higher. That's a directional selection. And so if you looked at the curve here, the normal distribution of giraffes, and you looked at neck length, this would be number of giraffes. Over time, you see that this has been shifted to higher neck length is the average. Okay, that's a directional selection. But there is going to come a time where the longest neck giraffes actually are starting to get a disadvantage. I mean, this becomes an unwieldy trait at some point. I mean, giraffes can only get so tall before they can no longer drink water, which is, generally at foot level. So, like water's down here. So once the giraffe neck gets too long, all of a sudden it becomes a negative. Like they're not actually able to survive any longer if their head gets too far up off the ground. So I mean, giraffes already have to do a really weird body position in order to get water. They have to like kind of bend their front legs and kneel forward, and it's already a tough task. So there is a maximum height here. So what ends up happening is, as this neck length shifts and shifts and shifts, suddenly you start running into an area over here where this is actually too long. Okay, so So this area starts exerting another selective pressure in the opposite direction. So in other words, there's a max. And once you start hitting that max, then what starts happening here is stabilizing selection. So a different type of selection starts operating on this organism, where you still have the pressure for longer neck to get to the high acacia leaves of the tree, but there's also a selective pressure on the other side that says, okay, if you get too tall, you can't drink water anymore and you can't move around properly anymore. Your neck is too long. And then so what ends up happening now is that as the generations go on, you start seeing a focusing of the traits towards the middle. Okay, so then the Norval curve actually starts getting more and more pointy as the neck length moves towards an average, as opposed to being directionally selected. Okay, so when you say, like how one-sided can the pressure be? It can be one-sided all the way up to the fact that it becomes untenable as a trait. And then there's going to be a selective pressure pushing in the opposite direction. The same thing happened to the stock-eyed fly. So if you remember that example, that's an example of sexual selection, but we've got these like weird eye stalks on the end of the fly. And it's a real crazy, I'm going to do a terrible job drawing this fly, but there's my fly. So we've got this really weird eye stalks. They can only get so long. So once they start getting so long that the fly can no longer live properly, it can no longer like navigate, it's too susceptible to predators because it just has a real funky head where it just can't, it's untenable. So then all of a sudden you get that selective pressure on the other side pushing it back, and it becomes stabilizing at a specific spot. So these pressures are always working on animals or plants, every species, and usually over time, if the environment is stable, the type of selection that operates is usually stabilizing at some point. It becomes stabilizing over time. Now, here's an interesting situation where that does not occur. So imagine that you have a snake, and this is a real life example. Okay, so you've got a snake that. Oh, I'm gonna do my best to draw a snake here. You got a snake, and then you've got a mongoose. Okay, so the mongoose, which is a mammal, I believe, is like a little creature, and the mongoose has extremely fast reflexes, mostly for avoiding snakes. Oh, I'm so sorry about this. This is going to be a terrible drawing of a mongoose. Okay. And what happens is that the snake is attempting to kill the mongoose, which is its predator, via strong venom. Okay. So the snakes typically that have the strongest venom are the snakes that are going to survive. Okay. So what this is going to start off with here is a directional selection. Okay, so we've got venom strength, and most traits form a normal distribution unless there's disruptive selection happening where both sides are potentially a benefit to the animal. Don't forget that that's an option as well. But in general, you see this normal distribution. Let's say this is venom strength for the snake. So what happens is, this is number of snakes. Okay, so what happens over time is as the venom strength of the snake goes up, that actually means that for the mongooses that have the strongest resistance to venom also goes up. Okay, so over here, what we get is increased resistance to venom. Okay, so then the mongooses that have the best venom resistance are the most likely to survive. But what happens there is that the mongoose's population becomes more resistant to venom. So on the snake side, they have to increase their venom strength again. Okay, then for the snakes, then again, the most venomous snake is going to be the ones that survive the best because they're the ones that can combat the resistance in the mongoose, which means that the mongoose is also going to have to increase its resistance. Okay, so then the ones with the most resistance will again be selected for, which means that the snakes with the strongest venom will be selected for, which means that the mongooses with the highest resistance will be selected for. And over time, this is called an evolutionary arms race. What happens over time is that you get a super duper venomous snake and a super duper resistant mongoose, which is how this actually works. This has actually played out in nature. In other words, the selective pressure here for the snake venom is just a continuous pressure pushing this way over off the screen. Okay, it just keeps getting more and more strong over time. The snake venom eventually is going to start becoming stabilizing because there's going to be something about increased venom strength that is going to be detrimental for the snakes, but they haven't hit that barrier yet. So when you have a situation like this that arises, and by the way, Australia is a great example of a place where this happens a lot, which is why Australia has such a high incidence of extremely venomous animals, because you just see these evolutionary arms races playing out all over Australia. So they have, a number of extremely venomous snakes. They have a number of extremely venomous spiders. This arms race is the reason why you see those things. Why would a creature ever need venom that could kill a human 50,000 times? Like that, there's no reason to evolve towards that level of venom strength, except there is a target species out there somewhere that's highly resistant to their venom. So that is what's been pushing them to continuously evolve this stronger and stronger venom. That's why you get these crazy venomous snakes. It's not because of humans, but there's always some target species out there that has high resistance. So anyway, that's an evolutionary arms race. I hope this is answering your question, by the way, Evan. But essentially, there is no limit until something about that, about evolving that trait more in a particular direction is untenable for the animal. So a good example here would be the giraffe is going to hit a max neck length here. Okay, and then it will become stabilizing. But sometimes that doesn't happen for a really long time, and so you get this crazy arms race happening. Okay, sorry, that was a little bit of a sidebar. So what we were talking about here is this idea of the grass. I still didn't answer this question from the text. Sorry. This is important, though. This is also an important concept. So we've got this grass, and there's multiple opportunities for this grass to evolve. So it could potentially move in to this rocky area over here, in which case it would need a shallow root system, maybe a root system that is specifically adapted to living on a rocky surface. So in that case, there's going to be an adaptive radiation that occurs that is grass with maybe a complex root system. Okay, so you're going to end up with some kind of crazy fibrous root system that grows out the plant. And the standard plant doesn't have that. It just has a taproot. Okay? And then there's also going to be an area where it's very muddy and swampy. Okay, so let's say that that's like over here on the island, and that also doesn't have any of these plants growing in it. And so in order to adapt to that, the plants that have surface roots that are growing up high, maybe even above the surface, that exists as well, are going to be adapted here because otherwise their roots are going to drown. So we're going to have another radiation that goes out this way, where we've got a grassy plant where the roots are maybe even going to grow up. Okay, so we've got roots coming out of the ground, and that's going to support a really muddy environment. Maybe there are areas where there are native plants that are low-lying, okay? And in that case, this plant has to adapt. So let's say that there's some other shrubberies here, low-lying shrubberies. And in order to compete with these low-lying shrubberies, the plant has to grow taller leaves, okay? So we end up getting much taller leaves to compete with the low-lying shrubs. Okay, so that's another adaptive radiation from here. And so what ends up happening over time is that one particular ancestor species is going to end up with all of these really different offspring species. And these are so different from one another, this one and this one and this one, that they can no longer interact and reproduce. So that's the reproductive isolation that we talked about previously. Maybe their seeds are going to be different or whatever. Something's different about these plants that they can no longer interbreed and produce fertile offspring. That's an adaptive radiation. So the situation that was described here, so 30 species of related plant, okay? Essentially what they're saying is there are 30 different ecological niches that these plants have moved into. They've formed completely new species in each of those niches that are no longer able to survive or reproduce with the other groups. And so then you get that is an adaptive radiation. Okay, and the reason that these are found nowhere else on Earth is because this evolution occurred on this island. So, and islands are typically, especially Pacific islands, quite isolated. And so there's no way for the seeds from these plants to make it to the mainland, to make it to a subsequent island. Or maybe a neighboring island shares some of these plants, but no other islands. Because seeds cannot be transported perhaps that distance. Okay? Over time, maybe if we looked, 10,000 years in the future, we would find these plants on other islands or even on the mainland somewhere on a large continent, because there was an incident where these seeds have migrated from, I don't know, a bird or whatever. Okay? But there was one specific incident that allowed that original ancestor to come to the island, and then an adaptive radiation occurred, and all of these subsequent species evolved on that island. But the evolution was contained within that one island. And this is a great piece of evidence for evolution, is that we have these adaptive radiations that exist in isolated environments. And to some extent, Australia is that isolated environment, which is why we get these unique situations happening like this. I'm hoping that I answered that question, Caleb. And where do you make distinctions between same species population groups? Technically, Eben, we're supposed to make the distinction when we're talking about whether the pollen naturally, through whatever pollinator species is able to, through a natural process, reproduce and produce fertile offspring. So if you can take a tree on the east coast of Canada and the west coast of Canada, and they would naturally reproduce with each other with a pollinator in nature, we would call that the same species. Okay, so it's not a different species if you can have natural reproduction between the two groups. However, so that's the official answer. However, in real life, biologists don't adhere to those rules as closely as they should. And so sometimes, even though they produce fertile offspring in nature, because they may look different significantly, we just decide to call them a separate subspecies. And sometimes these are totally artificial designations. I wish I had a better answer for you here. This is like a weird exception in biology where this isn't like a really hard and fast rule, because there are species that look, relatively similar. Maybe they have a different bark pattern or some different configuration of their leaves or needles or whatever. And we've decided artificially to say this is a separate species or a separate subspecies, even though they can reproduce with their closest neighbor and produce fertile offspring, even in a natural setting. So a good example of this is the grizzly bear and the polar bear. Those two bears, and we talked about this way, way back at the very beginning of Unit 1, they look different, yes, but they do reproduce naturally with each other and produce fertile offspring in nature. There is overlap between the ranges of polar bears and grizzly bears, especially there's more now than ever because polar bears are starting to move south because of the melting Arctic ice. So these groups interact with each other. They reproduce with each other. They make fertile offspring. So by every official definition of species here, the grizzly bear and the polar bear really are the same species. They naturally interbreed. They produce fertile offspring. However, they look significantly different. They have significantly different behaviors Their hunting behavior is different. Their hibernation behavior is different. And so because they are morphologically different from each other significantly, we just call them a different species, even though they don't really officially meet that definition. So I want to give you a really hard and fast rule here, Evan, on the reasoning for that, but I actually can't because it just doesn't exist. So I'm speaking generally here. If they don't survive and reproduce, or sorry, if they don't reproduce and produce fertile offspring naturally, those are definitely separate species. But sometimes they're separate species, even if they do that, because we just ignore the rules sometimes. That's a remnant of the old way of doing things in biology, and there's a lot of that going on. We still make a lot of taxonomical groups based on things looking similar, even if they're not closely related. That's a leftover of like the old way. That we're doing less and less. So what I've found is that over time, even over the past 15, 20 years, we've moved towards a much more scientific model of determining these things. But there is still a lot of leftover from biology from 100 years ago, where we still do stuff like that, where I can't really give you a good answer. Anyway, I hope that answered your question. It doesn't have a clear answer. So anyway. Are there any other questions before I move on here? That was a very long-winded response, but I do think it touched on a number of things that we've been discussing, so that's fine. Okay, so I will give you guys an opportunity to work on the human evolution content in the afternoon. If you have any questions from that, you can always post in the chat. Find me during the Google Meet at 1, or you could just always ask at the beginning of class tomorrow. I'm happy to answer. If you finish these early, and I know a number of people probably already finished, please double check to make sure you have all your quizzes and assignments complete. And we got to get that done today, guys. Everything from plants has got to be in today. So, especially because tomorrow is the end of the last unit, and then you got to have everything in for that one. So don't put this off. I intentionally made the second part here pretty short, so this probably shouldn't take you more than an hour. Anyway. If you're interested in doing 10 minutes of meditation, highly recommend it. I'm going to do that now. And if not, just mute. You guys can move on. Okay, let's do it. As soon as I get this going. Just give me 1 second, guys. This website always has a real tough time loading. Let's try reloading this. All right, here we go.
So as you just take a moment or two to get comfortable, just setting up the exercise with the eyes open. Without moving the eyes, make sure you can see the space around you, either side, above, below. And just maintaining a very soft focus. Just beginning with some big deep breaths, breathing in through the nose and out through the mouth. And as you breathe out this time, just closing the eyes, allowing the breath to return to its natural rhythm. Beginning to feel the weight of the body pressing down, and different points of contact. Just settling into that space. And beginning to notice different sounds around you, just allowing those sounds to come and go. And bringing the attention back to the body now. Noticing any sense of heaviness or lightness in the body. Noticing if the body feels at all restless or perhaps particularly still right now. And then starting at the top of the head, just scanning down through the body, all the way down from head to toe. And as you become more aware of the body in general, starting to notice the breath, the movement of breath. Begin with just in a very general way, noticing which parts of the body move, that rising and falling sensation. And continuing to follow that movement. Beginning to notice each and every breath Noticing if the breath's long or short. Following each in-breath and each out-breath. And as you continue to follow each breath, just to help maintain that focus, just counting the breaths as they pass, realizing when the mind's wandered each time, just returning to that sensation. So as soon as you realize the mind's wandered, just gently coming back to the breath each time. And now letting go of that focus, just for a moment, allowing the mind to be free. And as you bring the attention back to the body now, just coming back to that feeling of weight, of contact, coming back to the space around you, the sounds, the smells, just becoming more familiar, that space, the way you feel, posture. And then when you're ready, in your own time, you can just gently open the eyes again.
I hope that was restful for your mind. And again, if you guys need anything, let me know.